Today I'm going to talk about the impact of climate and weather on the economy. I'm going to start with a controversial statement. Climate matters and climate matters to the economy. If not, we would worry less or not at all about climate change, but obviously a lot of people do. Now, saying that climate matters to the economy is not the same as climate determinism. Climate determinism is a very old theory. It goes back to people like Guanzhong and Hippocrates and Aristotle and even Khaldun, but also to modern writers like Ellsworth Huntington and Jared Diamond, who all argue in various ways that climate and geography ultimately determine the political and economic success of a nation or a people. I do not believe that at all. I do believe, however, that climate matters. The claim that climate matters to the economy is controversial because the mainstream of economics believes the opposite. The people who have studied long-term economic growth, or who have studied the pattern of economic development across the world, who is rich and who is poor, all argue that climate and geography are irrelevant. Danny Roderick and colleagues even have a paper entitled Institutions Rule. What matters to economic development is the rule of law, the quality of education, and so on and so forth, rather than climate and geography. Darren Acemoglu and Marcella Alsan take a slightly more nuanced position. They agree that institutions are very important, but they also argue that institutions are shaped by the climate of the past. However, they also find or argue that as soon as this shaping is complete, several centuries ago, climate is no longer important. Climate was important in the past, but it is no longer today. Now, if this were true, then if we were interested in the economic impact of climate change, we actually do not need to worry in the very long run. May have some transition issues, but in the very long run, climate is irrelevant and therefore climate change is irrelevant. A somewhat peculiar position according to most people who are not economists. It's also completely wrong because climate matters. Climate matters obviously for agriculture, it matters for energy demand, it matters for tourism, it matters for health, it matters for labor productivity. And more recent papers show that climate indeed explains, in part, the income distribution within countries, not just between countries, but also within countries. And within countries, of course, institutions are much more equal than they are between countries. Yet these cross-sectional studies are problematic from an econometric perspective. And the main issue here is causality. Climate changes only very slowly over time, and it hasn't changed much over the period over which we have very good data. And of course, many other things that we know are important for economic development and economic growth have changed over that period as well, and sometimes much faster than climate has changed. Climate varies much more strongly over space, but also there many other things that we know are important for development change over space as well. So it is just very difficult statistically to pinpoint climate as a potential explanation for what we observe. To overcome this, people have turned to studying the impact of weather on the economy. And by now there is a long list of papers doing exactly that. The good thing from a statistical perspective is that weather is random, and definitely if you look at the weather from the economy, it is basically random. So you essentially have a natural experiment, and therefore claims of causality are very easily made. I think that should be taken with a grain of salt. By now, we know that weather affects a large number of economic, a large diversity of economic activities, which of course all affect one another. So I think we should be a bit careful with our claims of identification there, but it has by now been very well documented that climate affects at least some economic activities directly. It has also been documented that weather affects economic growth, that the economy grows more slowly when it's hot. There's two strands of literature here. The first and older one, associated with Melissa Dell, finds that this effect is stronger in poorer countries, whereas the other strand of literature, associated with Marcel Burke, argues or finds that this effect is stronger in hotter countries. But in sample, it's actually very difficult to distinguish between these two types of models, and that is because most poor countries are hot, and most hot countries are poor. So you really identify the effect of only a handful of cold but poor countries like Mongolia, or rich but hot countries like Qatar. So within sample, it is very difficult to make this distinction. Out of sample, there is a big difference between the two models, because we expect the future to be hotter but also richer. According to the Berg line of models, vulnerability to weather shocks increases as the world warms, whereas according to the Dell line of models, vulnerability to weather shocks decreases as the world grows richer. So out of sample, there is a big difference between these two models. The problem with studying the impact of weather shocks on the economy is its extrapolation to the impacts of climate change. Weather is not climate, weather shocks are not climate change. Climate is what you expect, weather is what you get. At the root of the problem here is that there's very little you can do against the weather. You can put up your umbrella, you can close the floodgates. On the other hand, you can do great things against climate and climate change. You can buy an umbrella and you can build those floodgates. In other words, if you estimated the economic impact of weather, you've estimated a short-run elasticity. Whereas if you want to study the impacts of climate change, what you need is a long-run elasticity. And short-run and long-run elasticities are simply not the same. Two papers lay out the conditions under which weather impacts are informative about climate impacts. Tatjana de Hugenaar and Solly Xiang show that these conditions are the same as the conditions under which a market is a Pareto optimum. Full divisibility of goods, fully informed rational agents, no externalities, no public goods. I see this paper as an impossibility theorem. Irrigation, a key adaptation to climate, is a lumpy investment. Coastal protection is a public good. Infectious disease causes externalities. Derek Lemoine goes a step further. The key difference between weather and climate is the malleability of capital. You cannot just close the floodgates, but you can build them. Now, Lemoine shows that you also need to have that expectations of the future are perfect, that we actually know what is going to happen. And we've seen time and again in empirical studies that people have a very peculiar perception of the weather and of weather forecasts. Two examples. First is backyard snow. People go skiing when it's snowing around their house. They do not check whether it's actually also snowing in the mountains. Another example, people buy more open-top cars when the sun shines. What matters is, of course, the expected weather for the duration over which you plan to own the car, rather than the actual weather at the time that you buy the car. People have very irrational expectations of the weather. And for all those reasons, we learn very little about the impacts of climate change if we study the impacts of weather shocks on the economy. So what I'm going to do in this paper is simultaneously model the impacts of climate and weather on the economy. Conceptually, the paper is fairly straightforward. I'm going to explain this with an example from agriculture. If you want milk, you need a Holsteiner cow. They are simply the best at producing milk. As the name suggests, Holsteiners are from Holstein, and that is the area of southern Denmark and northern Germany, and it has a rather cool climate. And if you take a Holsteiner out of its native climate and bring it to, say, Thailand, it's fairly unhappy, it's way too hot, and it simply produces not enough milk. The picture that you're looking at is not from Thailand, but from South Carolina, where it's also pretty hot. And the only way to keep the animals happy and productive there is to water cool them. So production is good, but of course your costs have gone up. Now, if you want to grow rice, and particularly jasmine rice, that most people consider to be the best rice in the world, then Thailand is the place to be. It's a bad place for milk, but it's a good place for rice. Vice versa, if you want to grow rice in Denmark, well, good luck to you. It simply won't work. So climate affects what you can do in your economy, not just with agriculture, but with many other things as well. Weather, on the other hand, affects not so much what you could do in your economy, but how it works out in a particular year. You may have a drought and your crops may fail. That does not mean that it is a bad idea to grow those crops in the first place, but in this year it turned out you had bad luck. Or you may have floods, block your roads, wash away your bridges, and that is a temporary disruption of your production in that particular year. So the natural way, at least to me, to think about these things is to put climate in the frontier, in the production frontier, and put weather as a source of temporarily inefficiency. And that then automatically leads us to stochastic frontier analysis. So the model seeks to explain output per worker for some 160 countries for a period of 65 years. In the frontier of the model, I'm going to put capital per worker, essentially how much machinery and everything there is available, and then the climate variables. And then I'm also going to explicitly model inefficiency, and I'm going to put the weather in there, specifically temperature and rainfall anomalies. The method I'm going to use is stochastic frontier analysis. One of the three conditions for an efficient market is production efficiency. This essentially means that producers cannot rearrange their inputs to generate more output. And that then leads to a production frontier. And you cannot do better than this production frontier. Obviously, this frontier is imperfectly observed. There's measurement error, and there's all sorts of idiosyncrasies in your companies. But if you try and estimate this thing, take it to the data, you will also notice that there's actually firms that are far away from the frontier, which is theoretically impossible, but of course we never observe the economy in an equilibrium. We only take a snapshot of an economy in this equilibrium. So the assumption here is that those firms who are far away from the frontier are either on their way to going bankrupt, or perhaps they're on their way to being taken over by another more efficient firm, or perhaps they are about to reorganize themselves. Now, the way stochastic frontier analysis deals with these two things is that it has a composite error term. There is a two-sided idiosyncratic error, that is essentially your imprecision in measuring the frontier, and there's a one-sided error that essentially tells you how likely it is that a firm is away from the frontier, that it's an inframarginal producer. And that looks something as follows, and this is the specification that I'm going to estimate and show you the results of using Bill Green's true fixed effects model. It's essentially stochastic frontier analysis with panel data and fixed effects. And in the frontier, I'm going to try and explain the logarithm of per worker output. This is a function of the amount of machinery they have, then temperature and temperature squared, rainfall and rainfall squared, and their product. And this is the 30-year average. So in the year 2014, it is 1985 to 2014, the average temperature and rainfall over that period. And there's a trend, and there's a country dummy, and then this is your standard error term that you would see in a regression. So this is the measurement error or the idiosyncratic error. And then there's another error term which captures inefficiency, and that is denoted U. And U is assumed to be distributed according to an exponential distribution with a parameter lambda. And that lambda is a function of, again, a country dummy and the absolute deviation of the actual temperature from its long run mean and the actual rainfall from its long run mean, and both are standardized by the standard deviation of temperature and rainfall. So this is essentially the standardized temperature and rainfall that goes in there, and we take the absolute value of this. This is the model we're going to estimate. As you may have guessed, this is a highly nonlinear model. It's computationally very cumbersome. We used Stata to do so, particularly Kumbakar's SF model, and that's how we estimated the model. I already gave you the specification. There's a whole bunch of robustness analysis half normal instead of the exponential, squared anomalies instead of the absolute value, and so on and so forth. And of course, we're also going to introduce heterogeneity in income and climate, because that is one of the things that people in the literature are not quite sure about. And then I'm also going to talk about a key concern that we have in all this, and that is the non-stationarity, the non-stationary nature of both dependent and independent variables. So let's look at some of the results. Here are 6 alternative specifications for the frontier. Capital per worker is always significant, parameter is always around 0.63. Temperature and temperature squared are always significant. Rainfall, R, is not significant unless we include the interaction between temperature and rainfall. Then the 2 rainfall parameters are significant. Similar story for the interaction with poverty, P, that only becomes significant if we include the interaction between temperature and rainfall, but the interaction with temperature is not significant. Now, if we move to the inefficiency term, the weather anomalies in the richest model are significant and negative. The interaction with poverty, P, is statistically significant, and the interaction with heat, H, is also significant. I previously talked about the debate between Burke and Dell. Is it heat or poverty that makes you vulnerable to climate change, or to weather shocks rather? And the answer, according to this model, it's both. So they're both right, or both half right. This is a very complex model. There's all sorts of things going on. There's rainfall anomalies, there's temperature anomalies. They have different effects on different groups of countries. And then there's temperature and temperature squared, and the interaction between temperature and rainfall and rainfall and rainfall squared, right? So it is a very complicated model. It's hard to make sense of what is really going on here. So I drew some graphs. In red, we're looking at the effects of temperature. In blue, we're looking at the effects of rainfall. On the left, we're looking at the effect of changes in the frontier. And on the right, we're looking at effects in the inefficiency term. The size of the circle is the number of people in a particular country, and we're looking at results for all countries of a 3 degree Celsius warming by the end of the century, or a 3 degree warming per century for the weather shocks, and a 20% wetting over the same period. The effects on the frontier are here expressed as a function of the current temperature. So this big circle here is in a warm place, this is India. This big circle here is in a colder place, that is China. What you see is that colder countries see a positive effect, hotter countries see a negative effect of climate change. No surprises there. And then these are the rich countries where you see actually a more pronounced effect. For rainfall in the frontier, you don't see a lot of structure here. Move to the weather shocks, and these are weather shocks, but of course in a scenario that is warming, what you see is that unusually hot weather becomes more likely, and unusually cold weather becomes less likely. So you see actually an increase in weather shocks as well, even though it's weather, but that weather is of course affected by climate. And you see 3 patterns here, and we express this as a function of the current variability of the temperature. And what you see is that the effect is more pronounced if the weather is currently less variable. No surprises there again. If your weather is always the same, it doesn't vary a whole lot, climate change will actually bring pretty unusual stuff. Whereas if your weather already varies a lot now, then climate change would have to work much harder to surprise you. So in countries with a variable climate, the effect of climate change is actually smaller. We see 3 patterns here. We see the hot and poor countries, this is India again, have fairly negative effects. The scale here is the change in output per worker by the end of the century. So 0.85 means a 15% loss of output per worker, so a 15% loss of income as well, if the number of workers per capita stays the same. So that is a fairly large effect. Then in poor but temperate countries, we see also a negative effect, but that is much smaller. And then in rich countries, we actually see a positive effect of climate change. Same pattern pops up for rainfall, positive in the rich ones, small but negative in poor but not so hot places, and fairly negative in the hot and poor places. So that is the pattern that we see. Warming has a positive effect in cold countries, a negative effect in hot countries. Wetting has mostly a positive effect. The problem is too little water, not too much. The effect of weather shocks is negative in poor and cold countries, very negative in poor and hot countries, but it's positive in rich countries, and that may be puzzling. I think that the reason here is that we measured output per worker as in terms of gross domestic product. And what we're really seeing here is Bastiat's fallacy, which is if you break a window, you don't have any effect on GDP. But if you repair the window, you increase GDP because that is economic activity. Of course, what you should do is use net domestic product rather than gross domestic product. But the problem with net domestic product is that you don't have a lot of data. So you can't do that. The reason that Bastiat's fallacy shows up in rich countries but not in poor countries has to do with the structure of government support and insurance. In rich countries, if a bad weather shock happens, if a natural disaster happens, then insurance starts to pay out almost immediately. Government starts releasing its reserves and start repairing things almost immediately. In poorer countries, this takes much longer. The repair effort is spread out over a much longer period, if it happens at all. So in rich countries, you would see this positive effect of the repair activities, but in poor countries, you would not. And that may explain this positive effect that we see of unusual weather in rich countries. I showed you the effects on every single country. This is the effect of all countries put together. Now as a function of climate change. Frontier is here. We go up to 6 degrees of warming. Unlikely, but it may happen, right? And what we do in this particular graph is simply add up the dollar terms for every individual country. In the dotted line, we account for the fact that $1 to a poor woman is not the same as $1 to a rich woman. And we apply so-called equity weights, and you see a slightly stronger effect and slightly more linear. Things change very much if you look at the inefficiency term. The inefficiency term, weather shocks were positive in poor countries, recall, and positive in rich countries dominate the world economy, so we see a net positive effect for the world as a whole. Unless we equity weight the results, then you see a very substantial negative effect. So it's the poor countries that get clobbered here. So this is for temperature. Here we're looking at rainfall. The frontier is here again, the equity weighted frontier, qualitatively the same. You see a fairly large effect on the economy for wetting, and a fairly large and positive, fairly large and negative for a drying. For the inefficiency term, what really matters is how you deviate from your expectations rather than whether it's hot, whether it's wet or dry. So you see this kink here, where actually it's symmetric around no change. For the scenario where we just add up dollars, you see positive effects everywhere. Again, this is dominated by what is going on in the rich countries, but if instead we equity weight the results, you see small and negative effects, whether it gets hotter, whether it gets wetter, or whether it gets drier. So those are the global impacts. We made a lot of assumptions in the model. And we changed them all. We replaced the absolute value of the weather anomalies with its square. We looked at linear anomalies. We looked at asymmetric anomalies. The results are qualitatively the same. We replaced exponential distribution with a half normal distribution. It doesn't affect the results, and that's for the inefficiency term. We put the weather in the frontier, did not really change the results, neither qualitatively nor quantitatively. The results do change quantitatively if we redefine who we classify as rich and poor.
No surprises there. We find very different responses there. So if you put countries in another group than they were originally, you would expect to find quantitative changes, but qualitatively the results remain. So we're pretty happy with this. In my introduction, I talked a lot about this institutional determinism that you see in modern macroeconomists. You could have expected, and you should have expected, that I actually address this particular issue. But I cannot do so directly. And the reason is that the indicators for institutional quality, for the security of contract, for the quality of higher education, and all those sort of things, the ease of doing business, the indicators for those particular aspects of institutional quality are available only for the last 15 or 20 years or so, not from 1950 onwards. Now, in recent times, those indicators actually correlate pretty well with an indicator for the structure of government, whether it's democratic or autocratic or somewhere in between. And that indicator is Polity 2, and the advantage of Polity 2 is that it goes back to the year 1800. So we included that particular indicator. And you see the results here. The results are not significant. It does not show up as important. Also, it does not really affect the parameters of our climate variables of interest. That is a bit surprising, but reassuring. It's not that we are really picking up an institutional effect when we were looking for a climate effect. Another thing that we tried was replace this poverty dummy. It's arbitrary and jumps from 0 to 1, somewhere in the middle of the sample. We replaced that with capital death as an indicator of the standard of living. That is significant, but it does again not affect the impact, the coefficients on our climate parameters. So this is all reassuring. The thing that we worry about, and worried about for a long time, is non-stationarity. Because the dependent variable, output per worker, is definitely non-stationary. It has gone up. And a lot of things on the right-hand side, the explanatory variables, are non-stationary as well. Climate change is essentially non-stationarity of temperature and rainfall. And in the model, in the estimator, both error terms, both the idiosyncratic errors or the measurement errors and the inefficiency term, are assumed to be stationary. We worried about this for a long time, as I said. There are no tests for co-integration of stochastic frontier models, let alone panel co-integration. So we just closed our eyes and applied standard tests that were developed for other models. I presented this work a while ago in another seminar where Rob Engel was present, the Nobel laureate, and he reassured us that his intuition was that these tests that are developed in other contexts would also be valid for our particular distributional assumptions. So I'm not sure that he's right, but always happy to hide behind somebody else on these issues. The reason that this is such a big issue is because stochastic frontier models are very difficult to estimate, and therefore you have to keep the model very small and simple. And particularly, we assumed a common and constant time trend for all countries. So let's look at two countries, China and Japan. Our data start in 1950, and in 1950, from 1950 to 1980, the Chinese economy was basically stagnant, while the Japanese economy grew like gangbusters. Then, from 1980 to 2014, the second half of our sample, the Japanese economy was basically stagnant, whereas the Chinese economy grew like gangbusters. And in this assumption here, essentially what we do is we say, well, these two economies grew at the same rate as each other and at a constant rate over time, which is just obviously not true. And therefore it is no surprise whatsoever that we fail and fail spectacularly panel co-integration tests for our model. If you look at the frontier or the inefficiency or the two together. Also true if you estimate the model in first differences. Actually, the specification is different if you estimate the model in first difference, but the problem doesn't go away. And it is a problem, right? Our output per worker is indeed
non-stationary as is capital per worker. However, our temperature variable and our rainfall variable and our weather shock variables are stationary. So you could argue that the problems of non-co-integration that are very much there, and therefore the risk-spurious relationship, has to do with the misspecification of output per worker, capital per worker, and our time trend, and has nothing to do with our stationary variables, namely the effect of climate and weather. And that may reassure you, or it may not. If it does not, we tried a different approach as well. And that is, we used an error correction model where we assume a long-term relationship between output per worker, capital per worker, and our climate variables. And this time, because this model is so much easier to estimate, this time we did include a country-specific time trend. So it's a richer specification in that sense. And then we have also a deviation from that long-term relationship, where we have a convergence parameter. So if you're away from your potential output, you go back, provided that your lambda 1 is smaller, in absolute value is smaller than 1. And we have our weather shocks here. So essentially what this says is that there's a long-term relationship between output and climate, but that long-term relationship can be disturbed by weather shocks, essentially. That pushes you away from your potential output and creates an output gap. But when that happens, you actually convert back to the long-term relationship depending on the size of the estimated lambda 1. So this is a simpler model to estimate. Co-integration tests are definitely valid here, and we pass them, right? This model is the correlations we find in this model are not spurious in the Engel-Granger sense of the word. The model is also much more parsimonious. What we find is a parabolic relationship between the long-term, in long-term relationship with temperature, but not with rainfall. That drops out. It's still stronger in poorer countries. We also find that temperature shocks, but not rainfall shocks, reduce growth, but only in poor countries. So the puzzling effect of the positive effect on rich countries disappears. So it's a much simpler model, far fewer parameters that are significant and therefore needed to understand about the effects of the model. So here are the same graphs. The blue graphs disappeared because rainfall is no longer important. What we see again is a positive effect of climate change in cold countries and a negative effect of climate change in hot countries. That is one thing we find. And then for the weather shocks, we find no effect in rich countries, and we find a negative effect, small effect, in poor countries that is bigger again if you're less used to temperature variations. So this is for every country for a single climate scenario, and these are results for all countries put together, the global effect for a whole bunch of climate scenarios. And again, with and without equity weights. The short-term effects are very small. They're significant statistically, but not important economically. And long-term effects, if we just add up dollars, we actually find a positive effect in the short run, but a negative effect in the much longer run. But then we need to go up to 6 degrees. This is fairly unlikely, but then again, if we apply these equity weights, we say that the dollar is worth more to a poor woman than to a rich woman. We find negative effects everywhere, and fairly substantial negative effects for fairly drastic warming. So that is what we find. Climate affects the production potential of economies in both our specifications, the stochastic frontier model and the error correction model, and weather affects economic activity. And these effects are stronger and more negative in poorer countries. Now, what does this imply? First, if you worry about climate change and the impacts of climate change, there's two things you can do, not one. You can reduce your greenhouse gas emissions and therefore reduce future climate change. Or you can stimulate economic growth and thereby reduce the vulnerability to climate change. Both options are on the table, and our model again confirms this. So that may be good news. There's also bad news for previous work. Essentially what a stochastic frontier model does is it introduces heteroscedasticity. And in our specification, heteroscedasticity depends on the weather and therefore is related to climate. And that means that if you used a cross-sectional or a short panel to look at the impact of climate on economic activity or economic output or something like that, then you should have corrected for weather-induced heteroscedasticity. And if not, there's a good chance of bias in your results. Those studies that looked at the impact of weather on economic growth should have used a dynamic model, as in our correction model, but also our stochastic frontier model. Essentially what it says is if you have a particularly hot summer or a particularly dry winter, you have a negative economic shock. But the year after, when that effect is gone, you just bounce back to the frontier. And that is then recorded as rapid economic growth in the year after. So that is what our models say. If these models are right, it's a dynamic thing, not a static thing, as some of these studies have assumed that were published in the literature. And essentially the bottom line is that if our specification is correct, then most of the literature is wrong. And I end on that happy note.